All right, so we're going to start talking about static electricity. Right there from the name, static means stopped electricity, stopped electricity. In other words, we're going to be talking about charges, positive and negative, and their effects on each other, aka the forces between them. Now, to get to that idea, I need to remind you of an atom. So here's an example of a bunch of Bohr models of an atom. This is more the modern view, right, with the different orbitals. But Bohr models, all we have to deal with is energy levels, and it's a good approximation for what we're dealing with. Now, all charge comes from an atom. Electrons are negatively charged, and protons are positively charged. They're in the nucleus. The neutrons there, they don't matter in terms of this unit. They'll matter when we get to nuclear. Now, the unit of charge is the coulomb, right, the coulomb. So you'll hear I have negative 0.75 coulombs as a measurement of charge, how much negative charge you have built up. In other words, you've got a bunch of extra electrons around. The elementary charge is the, if you will, common denominator of all the charges. It's the charge of an electron or a proton, and you can't actually have anything that isn't in terms of electrons and protons. In other words, 3.5 coulombs, let's say, has to have a common denominator of 1.6 times 10 to the negative 19th. And whenever you divide that by, 3.5 by 1.6 times 10 to the negative 19th, you pretty much have to come out with a whole number. In other words, this is the charge of an electron and a proton. Now, the electron would be the negative out in front, but this is the charge of an electron and proton. They have to have the same charge for the atom to balance out, right? If this is the charge of an electron and proton, and all charge comes from electrons and protons, then everything has to come down to whole number electrons or whole number protons. You don't have half a proton thrown in there. So that's the elementary charge. Two ways you'll see charge being told to you is in terms of the elementary charge, especially if you're dealing with small numbers. You'll see something like 19e or 19 times the elementary charge. Or you might see, especially with larger ones, in terms of coulombs, like, what we said earlier, 0.75 coulombs, capital C there. And there are a lot, obviously, negative times 10 to the negative 19th, there are a lot of electrons or protons that have to make it up. I should also point out, while electrons technically can go free, and moving electrons is what we call electricity, protons don't actually flow free. We'll talk about the idea of flowing protons whenever we get into our circuits idea there and historical implications with that. But protons don't actually flow free. What's really occurring is something, an atom would lose an electron, making that atom a positive ion, and so we're dealing with those ions there. Another three terms that you should be pretty familiar with: conductors, insulators, and semiconductors. Conductors are elements, generally transition metals, so in between let's see, column 3 and column 12, and not even all of those. They are elements, conductors, that easily give up, and because they can give them up, they can also take on electrons. So in other words, there's enough electrons on the innermost energy levels that it will shield the valence electrons out there. In other words, keep the force from the nucleus from really reaching them, okay, letting the electrons get away easily. Insulators, on the other hand, especially a good example of this would be all your nonmetals, are really good about holding on to their electrons. They don't let them go. They keep them really close. Their valence electrons, they still have a good attraction on. Semiconductors, by themselves, without doing anything to them, actually act like insulators. But the trick with semiconductors is, if you put it in the right conditions, you can make it act more like a conductor. One of the really useful things with that is if you apply an electric field to it of a certain strength, all of a sudden at certain strengths, depending upon the semiconductor, they will stop acting like an insulator and holding on to their electrons really well. They'll let their electrons start to go free, more like a conductor, and so you could use it in a wire. That's actually what all of modern electronics is based off of, these semiconductors. Whether it's a computer, a calculator, a smartphone, anything like that is based upon the semiconductor. Now, Coulomb's law is where we're going to be spending most of our time in this unit here. Coulomb's law states the force between two charges is directly proportional to their charges. In other words, Q times Q. Q1 times Q is proportional. It's in the numerator to the force. And the force between two charges, so my force, is inversely proportional to the distance, R here, distance squared between them. All right, so R squared, how far between them. So as your distance goes up, force goes down by an idea of squared, right? So you go a little bit, not much happens. You go a little bit further, and all of a sudden you start having an exponential effect on it. And the two charges multiplied together, that's directly proportional to the force, nothing squared. K here is a constant. It's called Coulomb's constant, 9.0 times 10 to the 9th Newton meters squared per Coulomb. Sometimes you'll see that broken down into the permittivity of free space. We'll talk about that in class. But that's just a constant that you substitute into this equation. This equation is what gives you force. By the way, this equation can also be used. You use this to get a force. You can take that after you calculate a force, and you can do lots of fun things with it. If I have two protons, right, and there's a force between them because of that, I can then take that force and I can add it to other forces, right, using addition of vectors through forces. I could use that force, like we're going to in a problem coming up, as the centripetal force, allowing an electron to go around a proton, even though that's a overly simplistic understanding of the way the atom works. But anyway, I can use those forces for lots of things. Your electric force, or really I should say the electromagnetism force, it's one of the four fundamental forces. Electromagnetism, gravity, strong nuclear force, weak nuclear force. And it's interesting enough, the electromagnetic force actually tends to move. It's kind of weird to talk about how fast a force moves. It moves at the speed of light, meaning that if something's a really far distance away, it takes a little bit of time for the force to actually act on it. Gravity, now we're not sure fully about gravity. We think it moves faster than the speed of light. Hopefully more to come on that in a few more years of physics. This is something that you know intuitively. You've had this idea for a little while. Like charges repel. So positive and positive try to push each other away. Negative, negative try to push each other away. And something you found out in maybe a few of your relationships that you've had so far, opposites attract, right? So positive and negative, the forces are pulling inwards towards each other. Now, here's an idea of where charges live that some people find a little peculiar. Charge actually likes to live on the outside of whatever object it's on. So here I have an object with a bunch of positive charges inside of it, just right here like this. And they're swimming around, but think about the forces acting on them, right? Opposites repel. So, like charges repel, meaning all these positives are going to want to run away from each other. So they're going to split up. They're going to move out to the surface, trying to get as far away from each other as possible. Now, people have an initial reaction that they would kind of distribute themselves in the center of the sphere, or in the center of whatever object they might be existing upon. But if you think about it, let's take this charge right here. Whenever he's over here on the surface, these guys are the ones that are closest to him. Remember, distance is the force is according to the distance squared. So the further away you get, the less the force gets according to an idea of squared, exponential. So distance is going to matter more than charge. So he's only having to deal with these two guys mostly. These other ones are really far away. But if we move him more into the center, right, trying to maybe distribute it so it seems more equally, now he's experiencing a large force from pretty much everybody trying to repel him. So charge, because of this, likes to live on the outside surface of objects, which leads me to an idea called Faraday's cage. Faraday's cage simply states that if you were inside a conducting shell of some sort, whether it's wire, metal, or anything like that, all the charge, if you were hit with lightning or anything else, would distribute itself on the outside, and you would be perfectly safe on the inside, aka no electric field, no charge making it in there to you. So like this guy over here is testing it out. He has great faith in physics. You can already see the charge coming and hitting his Faraday cage and distributing itself down while he's perfectly fine. This is why when airplanes get struck by lightning, they're pretty much normally okay, because you have metal skin on the outside, the lightning, the charge is conducted around the outside and then might arc on down to the ground. This is why in a lightning storm, you're told to go get in your car. The odds of your car getting hit by lightning are actually pretty slim, but even if that did occur, that's okay, because the charge would live on the outside of your car, would flow around the outside, and then down into the ground. All right, so how do you get something charged? If you remember chemistry correctly, atoms like to live initially in a ground state, right, in a neutral state, if you will. But if you also remember some chemistry, they form ions through chemical bonds to try to get themselves to where they have 8 valence electrons, or a full outer shell. Sometimes it's other things, but normally 8 valence electrons with a Bohr model. So that's going to be a chemical idea. Batteries would be a great example of that. Another example of how you could charge something is by friction, actually rubbing electrons off of you onto something else or off of something else onto you. Think of taking socks in the wintertime and having them on your feet and scooting across the floor, building up a static charge to go shock your unsuspecting brother or sister. One way that tends to confuse people is called induction. Now, induction basically means you charge something by bringing another charged object close to it. So here's 2 examples of that. I have 2 metal spheres, A and B, and I bring a negatively charged object near them. Now, opposites attract, and like signs repel, right? So if I bring something negative, all of the electrons that are free to move about, if this is a conductor, 2 conducting spheres, are going to try to run off of sphere A and into sphere B, leaving sphere A more positively charged. Then, if I separate the spheres over here, that leaves a lot of positives on A and more electrons now on B, and so now I have 2 oppositely charged spheres. Positive and negative. That's charging by induction. Another one, if you're just dealing with one single sphere, I've got a neutral sphere. That means I have the same number of positive and negative charges inside of it. Here I'm going to bring another negatively charged rod. By the way, this could be done with positively charged objects. It doesn't matter. Because I bring a negatively charged rod in, all of the electrons will try, that are available to move, if this is a conductor, right, will try to move to the opposite side of this sphere or whatever object. Then if I ground it, aka I take a wire, I connect it to it and connect it to the ground, that gives a place for the electrons to escape, to be able to run even further away, right? So they run even further away down into the ground. When they do that, now this is left with a net positive, so whenever you take away the negatively charged rod, I have a positively charged sphere left over. All right, I'm going to work a couple of quick problems for you. A word of warning in this unit, you're going to start seeing some small distances possibly here, especially as we deal with atoms. Atoms lots of time are talked about in distances called angstroms, A with a little circle above it, if you will. Angstroms means times 10 to the negative 10th meters. You'll also hear picometers talked about, times 10 to the negative 12th, micrometers times 10 to the negative 6th, nanometers times 10 to the negative 9th. So don't be freaked out by any of those things. You see a unit you're not sure of, please open up your AP packet to actually see what that prefix on the meter, something meters, means there. Now, I have here a Bohr model of a hydrogen atom, 1 proton, 1 electron, and the average radius that an electron probability-wise will be from the proton, so this distance right here is somewhere around 0.529 angstroms. And I want to know how much force is existing between these two, because the proton's trying to pull the electron down, the electron will be trying to pull the proton up. So what's the force between them? Well, we use Coulomb's law. The electric force is K Q1, Q2 over R squared. And now I know K, Q1, Q2 over R squared. I just need to substitute in the numbers. All right, so I have K, 9.0 times 10 to the 9th, and then my 2 charges, right? The charge of a proton and charge of electron is the elementary charge. Now notice, I did leave my electron charge to be positive. Whenever you're dealing with electric force here, do the absolute value of the charges, aka make them all positive no matter what. And then you'll come out with a positive force, and you assign its direction manually there. In other words, if you know they're supposed to be attracting, then you assign whether, depending upon that direction, whichever it is, positive or negative. That will matter more whenever we start getting into 2D problems here. All right, so just know that you're going to assign the direction manually. Distance squared, notice the parentheses around that to make sure my calculator takes care of it for me. And whenever I substitute that into my calculator, I come out with 8.23 times 10 to the negative 8th newtons there. We will assume that the elementary charge, 1.60 times 10 to the negative 19th, is exact. Now, go ahead and get used to using the EE button on your calculator or the times 10 to button on your calculator, because you're going to have a lot of exponents, a lot of scientific notation that you're going to need to put in this unit and pretty much going forward in physics. Some really big numbers, some really small numbers. Remember, the elementary charge is going to give me the charge of the protons and electrons. Sometimes these charges will be in just normal coulombs, so you won't have to transition from a proton-electron charge, elementary charge, to the number of coulombs. If this was in a hydrogen atom, if this was, let's say, a helium atom, and I had 2 protons here, then I would need a 2 over here in front of this. 2 protons, 1 electron, force between my 2 protons and 1 electron if I was dealing with the nucleus to a electron. All right, while most problems that you're going to deal with are going to be basic problems like this, kind of plug chuggies for this first lesson, I do want to go ahead and solve another good physics problem for you using this idea. An electron in a Bohr model orbits around the nucleus of an atom in a pretty much circular path in the old Bohr model there, which means that this is centripetal motion. And the centripetal force, what's pulling this electron in, is provided by the electrical force, aka the attraction between the proton and the neutron there. So I can substitute my force in to centripetal force and solve for the velocity that this electron must be moving at. Now, the mass of an electron is a well-known entity. You just look it up in the book. It's 9.11 times 10 to the negative 31st kilograms. So after I work the algebra, I come out with the velocity of this electron. If it were going in a nice orbital motion, which we know it's not, it's more of a probability thing, to say the least. With electrons, the Bohr model does not hold. But if we assumed that, we'd come out with the electrons moving somewhere around 2 million meters per second, quite fast. If I were to get that in terms of speed of light, divide by 3 times 10 to the 8th, 3.00 times 10 to the 8th, that's about 0.7 c, or 0.7 times the speed of light, which is actually one of the reasons why the Bohr model breaks down. We're going to learn in electricity and magnetism that when charges move like an electron, it actually gives off electromagnetic energy. So it actually gives off energy, meaning that if it's releasing energy, the orbit of the electron would decay all the way down into the nucleus. So there has to be something else, aka the weak nuclear force to keep the electron there. The mass here of the electron might have thrown a few of you off. That's just a number you look up. The reason we're using the mass here in the centripetal force problem is, remember, mass and centripetal force is whatever is doing the orbiting, and it's the electron that's doing the orbiting around the proton. So that's why that goes in for the mass.